Hello, everyone. Welcome back. So now we are on lecture 5. We are going to talk about now solutions, solute, solvent, and solution. Okay, so an important part of chemistry is, making, doing chemical reactions that happen in solution. I think that's one of the most common ways chemistry is actually carried out. Um, in the lab. So we're going to discuss how solutions are made and what can we do with them, and learn some terminology about solutions that will be very important if you ever decide to carry over these lab skills into a career. Okay, so um, as we may know, substances, gases are very hard to work with because you can't really control them. So gases, they move very fast, so it's very difficult to work with them. So we can handle these gases if we kind of have them dissolve in solution. They're much easier to handle and much safer to deal with. Okay, so we dissolve these compounds, these gases, such as hydrogen chloride and ammonia, in water to form hydrochloric acid and aqueous ammonia, respectively. Okay? Okay. So when you dissolve something in something else, that's called a solution. It does not matter what the states are called. So it may sound a little bit peculiar that you may have a solid dissolved in another solid, but we still call that a solution because something is taking in another substance to form a uniform mixture. That is called a solution. Okay? Okay. All right. So some terminology here. The substance that dissolves in the solvent, that's called the solute. It is present in a smaller quantity. So, for example, if you boil water and you add some salt to it, you have created a saltwater solution, and the sodium chloride or salt is your solute, and the solvent is the substance that dissolves the solute, and that's the substance that's present in the larger quantity. So that would be a solvent. Okay. So any so a more kind of general definition is any reagent that undergoes a change in state when it forms a solution is called a solute. Um, and like I said, sodium chloride is the solute if you dissolve it in water. Okay. So if neither the component undergoes a change in state, like say you have a liquid dissolving in a liquid, the component that's present in the smaller quantity is the solute. So when we have wine or some alcohol beverage, is a certain percent of alcohol, right? Of ethanol. So we say that the ethanol is dissolved in. Well, we don't say dissolved, but it's miscible, meaning the two liquids mix to form a solution. They can kind of dissolve in each other. So we say wine is 12% ethanol by volume. So we say that the larger volume is the water, and that will be our solvent. And in this case, ethanol is in the smaller quantity, 12%. So it's the solute. Okay, some examples here are copper sulfate, pentahydrate, dissolved in water. We form a solution of the copper sulfate when we dissolve in the water. So we can have a gas. We can have hydrogen gas dissolved onto a solid, platinum, and we get a hydrogen/platinum solution there. And then mercury can also be absorbed onto sodium metal, and then you get what we call a solution of these two kind of like metals here, and that's called amalgam. So sodium amalgam, and there's also you can also do the zinc amalgam. So there's you could definitely form a solution of solids, liquids, or a liquid dissolved. A solid dissolved in a liquid. Okay, so those are some examples of solutions. The most common ones we'll work with are a liquid dissolved in another liquid, so a liquid dissolved in water, and a solid dissolved in water. So those are the two most common solutions we'll encounter. We will probably not encounter any of the other ones, like a solid, two solids. It'll probably be rare. Okay, so concentration. So we can reflect how much of the solute is dissolved in a solvent by calculating the concentration. So for this class, I will focus on two kinds of concentrations. The one is percent concentration. So like you have a percent of a solute dissolved in a amount of solvent. And then the one we'll talk mainly here is called a molarity. So briefly, concentration is the amount of either the solute, solvent, or solid solution in a sample. Well, it depends on the size of the sample, right? So you have more sample, more concentrated. So concentration is a characteristic property, so you cannot change the concentration by removing some of the solution. It does not change. The concentration will always remain the same. The only way you can change the concentration is if you somehow remove the solvent by evaporation or add more solvent to dilute it. So removing the solvent will concentrate it, like how you concentrate things, and then adding more solvent will dilute it, like, you know, when you cook, you add water to dilute the flavor so it's not too strong, etc. Okay? So the concentration, we could define it as amount of solute over amount of solvent or solution. So say you have a mass percent, right? You have 100 grams of solution and you add 5 grams of sodium chloride. That will be 5% sodium chloride solution. But most of the calculations we do here, previously you may have learned of concentration, like all sorts, molality, mass weight, mass percent, or mass volume percent. But most of the time in chemistry, we like to deal with something called molarity. So molarity, it basically means you're going to use the moles of your substance dissolved in a known volume of solution, and that will give you your molarity. So molarity is how we describe concentration of solutions. Okay, so it's defined as the number of moles of solute. So the number of moles, here per liter of solution. So we want to make sure we have a lot of practice doing molarity. So I set up a lot of examples in this lecture so we can practice that. So we can calculate the molarity by dividing the number of moles of solute by liters of solution, or the volume. So the volume is always in liters, and the amount of substance is always in moles. So we always use moles. Okay? All right. So copper, let's try this exercise right here. All right. So you see here, this is a volumetric flask. You may have seen these in the lab, so we'll probably use them to make solutions. So they're kind of like the volumetric pipette here. So you see that we have a calibration mark here. That's the mark that tells us where to fill the flask, and that tells us how much volume it will hold. So that's the 1 liter mark. So that tells us once we filled the liquid level to that mark, that will give us 1 liter of solution. So we'll also practice using this, I believe. So the copper sulfate will dissolve in the water, and then once you're done, this solution will be freshly made, and you'll have a solution of known concentration. Okay. So let's go on here. Okay. All right. So copper sulfate is a nice blue colored compound. if you add copper sulfate to water, you'll form a nice blue solution. It's very pretty. And that's due to the copper 2+ ion. So it has to do with how its electrons interact with light. Okay, so since we have 5 water molecules per C+ copper 2 ion, we call it a pentahydrate. So we saw the naming for these hydrates in class recently. So the formula, we write it as copper sulfate dot 5H2O to indicate that it's a hydrate, meaning that there's water molecules inside the crystal structure or the solid structure, or it's kind of interacting with the solid structure. Okay, so our goal here is to calculate the molarity of a solution prepared by dissolving 1.25 grams of copper sulfate pentahydrate in enough water to give us 50 milliliters of solution. Okay, so first things first, we're going to convert copper sulfate to moles. Okay, so remember that for the molar mass here, we have to add up all the numbers. So remember, you're going to add up copper, sulfur, oxygen. In this case, we have 9 oxygens, so oxygen times 9, and then 10 hydrogens, okay? So I'm not going to show the molar mass. You're expected to know how to do that, so I'm going to directly go to the molar mass here. So this should be a multiplication sign. Okay. So 1 mole copper sulfate 5H2O. So we must include the water molecules in our molar mass or we'll get an incorrect number. So we should get a number about 249.7 grams copper sulfate. So when we're doing molar masses, at least keep 1 decimal point. But I would keep 2. I decided to just keep 1 in this case, but you should use 2. Okay. So if we do that, we get 0.00501 mole. So we keep 3 sig figs in our answer because we have 3 figs to begin with in our measurements, 50 milliliters and 1.25 grams. Okay? And if students need to review significant figures, I would go online and look at some tutorial videos, but I think I might have posted a link in one of the Chem 300 review topics on Canvas. So there's a page for that. If you go to review material, otherwise students could come see me for review on sig figs. But I will probably not be going over it explicitly. It's expected that we understand how sig figs work and the general rules for the operations, math operations we use in this class, logarithms, addition and subtraction, multiplication and division. So those are the main. Those are most of the math. Those are the types of math we do in this class that are at the most basic level. Okay, so we found the moles of copper sulfate pentahydrate. So remember, once you're given grams, you can't use grams to find molarity. You need to convert to moles. All right, next, calculate the molarity by dividing the moles by the volume of the solution. Okay, so if we go down here now, sorry, it's on the next page, we do, so I'm going to 5.01 times times 10 to the negative third. So I'm just writing scientific notation now because it'll save me space on this line. Okay. So we know that we have 50 milliliters, right? So 50 milliliters. And we know that for 1,000 milliliters, we get 1 liter. So we have to convert the liters just because that's how the definition of molarity is. So that's just something we have to remember here. So here we get 0.0500. So you must keep these sig figs because if you don't, you will get confused when writing your final answer for the sig figs of molarity. So please keep 3 sig figs here. Okay, even though they're trailing zeros, you might be like, oh, that doesn't matter. But in chemistry, it does. We are a precise science. We are not a ballpark science. So we must always be very specific here, okay? So it'll give you good practice. Personally, I am not a fan of sig figs myself. I find them very annoying, but nonetheless, I must admit, they are very important. They are a very important concept in reporting data. Okay, so but the key rule is you want to make sure you keep all the sig figs until the very end. So don't prematurely round to a lower number of sig figs at the beginning, midway through the calculation. Okay. So we get here 0.0500 liters. Okay, and we should end up with a solution of 0.100 molar. So molar means moles per liter. So we put the capital M for molar. Okay, molar. All right. All right, let's try another one here. So how many moles of sodium sulfate are present in 250 milliliters of a 0.150 molar solution of sodium sulfate? So we can rearrange. So this equation here came from the molarity equation, which is molarity equals N equals moles. So here is mole over liters. In this case, moles equals N. So that's the variable for mole, and liter is V, which is for volume. Okay. So if we substitute those variables in here and multiply both sides by the volume, we get N. See, so the V's cancel out here, and we get V times M. So that's how we solve. That's how we rearrange the equation to solve for moles. Okay. So we know moles equals molarity times volume, which is equal to 0.150 mole per liter. And we know the volume is 0, so we could say 250 milliliters times 1,000. Oh, sorry, not 1,000. 1 liter per 1,000 milliliters. Okay, so milliliters will cancel, liters will cancel, and now what we're left with is moles, right? So if we solve for that, we will get N equals, so we don't have much room over there, so let's put it up here, 0.0375 mole sodium sulfate. All right. Okay, so that is sodium sulfate. So that equation we're given now, molarity and the volume of solution, so we can figure out the number of moles that are present in the whole solution. Okay, so we'll pick up lecture in the next video. So I'll see you then.